I think I'm going to start. I want to, I'm going to, as I suggested earlier, I am going to continue with 9 and 10, which is flame instabilities, and then leave tomorrow some of the other stuff. I'm sorry I couldn't cover everything. I had more notes than really. I mean, I knew that, but there was a matter of selection what to put in or not. I think it's useful that you have those, even if I didn't cover them explicitly in the class. But there is one last thing I wanted to mention about the theory that I have just described to you, or what I refer to as the hydrodynamic theory. I spoke a lot about flame speed and flame stretch. The question is, what happened with flame temperature? And so the theory still tells you that there is a dependence of the flame temperature. In other words, the flame temperature vary along the surface as a result of stretch. The thing is that the variations are very small. They are not only of the order of the flame thickness, like the correction of the flame speed, but they are flame thickness multiplied by the reciprocal of the activation energy, and so variations are very, very small. Nevertheless, they exist, and this is what the result from the theory is, that the flame temperature is the burn temperature, or the adiabatic flame temperature, corrected by stretch. There is a correction, in other words, but note that here it doesn't depend on the effective Lewis number. It depends on the Lewis number of the fuel in a lean situation and the oxidizer in a rich situation. And that's what also the numerical results show. So I will show you quickly two results. One is from DNS, numerical simulation of a spherical flame. This is the temperature as the flame advances. So it's the temperature profile at different, as a function of the radial distance at different time. So you see from T 3.75 to T equal to 9. If you look at the flame temperature, it looks almost like a straight line, but it's not exactly. If you zoom it, you see that there's a slight increase in slope. But the change, as I said, is indeed small. And so if you take experimental curve, for example, of a counterflow, which is shown here, clearly as you increase the stretch, then the flame is located, as you increase stretch, the flame is located closer and closer to the stagnation plane. So first it's located here, then here, then here, then here, and so on. But what was done, and this is taken from Ed Low's book, he simply superimposed all those profiles on top of each other to see if there is much of a variation in flame temperature. And you see that it's almost negligible, almost small. So it's consistent with what I showed you here, that even the computations show that it's nearly constant, but there is a small change. So first of all, in the hydrodynamic theory, we usually neglect those changes. Not to say that they are not important. I don't know what the consequence of that is because it was never studied, but I think it's an open and interesting question. The second thing I want to tell you is that the comparison between the numerical simulation and the theory, when does it increase or decrease? I told you that it depends on which of the two is fully consumed, the fuel or the oxidizer. Seem to agree very well with the theory. The theory is the red line, and the dotted points are the numerical simulation. So in those two cases, the temperature, flame temperature slightly decrease with increasing stretch, or it's better probably to say that as the flame expands, you're moving this way and the temperature increase, right, towards the adiabatic flame temperature, clearly. So it's slightly below. Similarly here, in this case, it goes down towards the adiabatic flame temperature. Okay, I have few other things here, but I'm gonna skip them. Perhaps just to say a few words about this. Remember that I told you that the flame speed is equivalent to an evolution equation for the flame position. So this is the evolution equation. If I replace now the flame speed SF with the linear expression SL minus L, the Markstein length times the stretch. So this is an equation often referred to as a G equation, but you have to be careful. This equation cannot by itself tell you everything about the flame, because you need to know the flow velocity, and the flow velocity is affected by gas expansion, and so you really have to solve this coupled with your Navier-Stokes equation. And another comment is that this equation is very good when the Markstein number is positive, but it fails when the Markstein length is negative. There's a pathological instability in the equation that doesn't help, and so the equation is useless when the L is negative. We can understand it in a very simple way. Suppose that K was the, suppose that we only account for curvature, let's say. So this term will give you a quantity which is like a Laplacian of F. And when curvature is going to give you a Laplacian of F. So approximately. So when the equation is like a heat equation, in other words, that the Laplacian is dissipating, then there's a solution. But if you have a backward heat equation, it's going to blow up. And so that's exactly what really happened, for L negative. So that's another comment that has to be made. Okay, using this equation coupled with the fluid dynamic equation give interesting results, and some of them I will describe later on. I'm going to skip this and the rest, and I want to move into lecture number 9, about flame instabilities. So first of all, I have a general comment about hydrodynamic instability in general. So so what I wrote that here, that if you have an equilibrium state, which is a balance between forces and so on, then that equilibrium can be disturbed by always disturbances that always exist in any system. And these disturbances can alter the equilibrium significantly. Or perhaps the disturbances are such that after they are introduced, they decay and they don't change the equilibrium. So when things are disturbed significantly, we call that an instability. For example, a very simple example, it's the upside down pendulum. In other words, the pendulum where the mass is on top, and let's say it's held with a massless rod. That's a perfectly well equilibrium. All the forces are balanced, but it's a very unstable one, because if you give it a little kick, it will start bouncing back and forth. Eventually, it will go down to the stable equilibrium, which is exactly the one which is with the mass down. So same thing in fluid flow. A small disturbance can alter the solution if the equilibrium is unstable. The way to describe instability, or the aim, is usually either, first of all, to provide a decision mechanism. In other words, is this equilibrium stable or not? And under what condition it's stable or not? And that's an important classification, because then it tells you if the equilibrium will or will not be observed, because an unstable situation is typically not observed experimentally, unless you take extremely good precaution to eliminate all disturbance, which is very difficult, sometimes not possible. And the second thing is we want to understand the transition from one state, one equilibrium to another. So the first part is usually determined by a linear theory, which we introduce small disturbances. Then we linearize the equation. We have a linear system of equation that determine for you the condition, if it's stable or not. We're going to see an example for flames. And the second part is more difficult because it involves discussing the transition which involve nonlinear effect. And that's usually a nonlinear theory or a bifurcation theory, which is schematically shown here. Suppose that the equilibrium is the red curve. It's stable on this part and not, it's unstable when the parameter exceeds a certain value. And at this point, it bifurcates into another form or a new solution. And so it involves talking about bifurcation theory and nonlinear theory, and it's more complex and involved. Of course, the bifurcation doesn't always have to be exactly of this form. There are different forms that it appears, but that's just an illustration. So in combustion, the instabilities that I want to focus on are what we refer to intrinsic instabilities, namely due to the combustion process itself. Of course, fluid mechanics can also cause an instability in a combustion system, but I will not focus on those. I want to focus on things which come from the combustion process itself. I mentioned earlier this week that the simplest problem of premixed flame, one-dimensional planar flame, doesn't have an exact solution, which makes it difficult already to analyze the stability, because most classical hydrodynamic stability studies start with a simple exact solution, like the Rayleigh-Bénard's convection start with simply that a fluid layer, you have just conduction, and then you ask, if you perturb that, when do the convection cells when is the onset of the convection cell? Now we are faced here with rather a difficult problem in combustion. And so the early work was by Daria and Landau, as I already mentioned yesterday, and they have treated the flame as a discontinuity. Rho U and rho B are the two densities. Essentially, they treated the flame as being represented by a surface across which the density change, which is the same thing as assuming that the temperature of the surface or the temperature is across is from TU to the adiabatic temperature. And they assumed that the propagation speed is just SL, contrary to, not contrary, but at the time they didn't have the more detail or what we have learned since. So they assume just that. So I want to start focusing on just this model, and then I will add to it what we have learned since. So those are two assumptions, and now what you do, you look at your system of equation. You have the Euler equation on either side of the flame. You have these jump relations, which is the Rankine-Hugoniot relation, and the flame speed is that it is a constant is equal to SL. The VF and N are geometric quantities, which we know that's a unit normal and that's a propagation speed. Now I wrote the equation that described the flame explicitly, x equal to a function of yz and t. In fact, I will only do 2 dimension, so it's going to be f of y. And so in this version, then the normal and the propagation speed are as written here. So the first thing to do is, this is to remind you that equivalent to this Rankine-Hugoniot relation, yesterday we saw that we can simply obtain the equivalent form, that the jump in the velocity is this, the tangential velocity doesn't jump, and the pressure drop is this, okay? We have seen that yesterday, that those two are equivalent. So I'm going to use this because it's just simpler to do. So the first thing is we want to describe the planar flame, then we are going to perturb it and study its stability. So the planar flame, in that, note that we already made this approximation of a thin flame, that it's just the surface. So now we have an exact solution in that context. So the flame is just, we described that yesterday. The incoming flow is the laminar flame speed, so that to retain the flame at a constant position, x equal to 0. The burn gas leave at a higher speed, sigma times SL, and the pressure is given here. So we know that. So the next thing is we introduce perturbation. The bar here is the planar flame. The prime are perturbation. So we perturb the flame, so also the flame surface is perturbed. Now it's the blue curve. And the next thing is we introduce this perturbation in the governing equation, the Euler equation, and we end up with these three equations, the x component, the y component, the continuity. Remember that in doing this, we have assumed that the perturbations are small, and so all quantities product of primes are quadratic or higher order term, and they are negligible, right? So the system is now a linear system. It's easy to see that these two reduce to Laplace's equation if you, the two momentum equation, just because if you take the x derivative of this and the y derivative of this, what you have here is u sub x plus v sub y, both time derivative, but ux plus vy is 0. Same thing, the uxx and vyx also is 0. So the Laplacian is 0. So an easy way to compute things is you solve for Laplace's equation for the pressure, then you compute the u velocity from the momentum, and then the v velocity from here. Okay, so this is a detail, and one can easily do that. But before finishing the problem, you also have to take the jump relation across the flame and also perturb them. Note that when you look at the small perturbation, the normal is essentially in the x direction with a small perturbation that it's the inclination of the normal, right? And this is the tangent unit vector. So these are the jump relation, and I want to spend a few minutes about them. Note that what it says is that the perturbation of the axial velocity is 0. In other words, it doesn't, there is no discontinuity, same value on the unburned to the burned side. The second one, which is the tangential velocity, has a jump, and it's because, again, the normal is get tilted, and so there is a jump, but the jump is proportional to the slope f prime of y. The third one says that the pressure disturbance, again, doesn't jump. This is an important one. It comes from the flame speed. It says that the flame, any segment of the flame is moving or propagating, right? F sub t, time dependent of the position, is propagating at the velocity, at the axial velocity. In other words, if the axial velocity increases, it pushes the flame. It decreases, it reduces the speed of the flame. Okay, we're going to touch on this again later, but these are the jump conditions that need to be satisfied. The next step that you do in linear theory, usually assume what is called normal modes. Normal modes meaning that you look for one Fourier component. In other words, the assumption is, the idea is that if you have a general disturbance, can be decomposed into Fourier modes. And since this is a linear system, it's sufficient to examine one mode because the general solution will be superposition of all the mode. So if you look at one general mode of the form e to the iky plus omega t, the k will represent the wave number so that the wave length of the perturbation is 2 pi over k, and omega is in general the growth rate. I is the square root of -1, so it's written in a complex form. And since we introduce a complex form, in general, omega may be complex, right? If we solve the complex system here, omega may be complex. Okay, if I'm going to keep the two-dimensional study or analysis. If you were to do this in 3D, there would be no big changes. The difference will be, instead of a wave number, you're going to have a wave vector, which is going to be a decomposition of two, K1 and K2, in the two tangential direction to the surface. And the K is going to be just the modulus of those. So that's a minor count. Okay. We are interested in the behavior of the system, right? So we have the planar flame perturbed, and what the perturbations say, it change, it grow or decay in time depending on e to the omega t. So what we are interested is essentially to examine the behavior of the solution after a long time. It decay or it grow. So omega in general, I said it's complex. Then you write it as omega real plus I omega imaginary. And so the form of the solution, this is like f prime. It should have been f prime, but anyway, it's not important. It's just for illustration. It's the amplitude e to the iky plus the imaginary part and e to the real part. So the imaginary part is just like a cosine and cosine. In other words, e to the I, anything is bounded, right? So the only thing that may grow in time is the real part. So the question for instability is whether the real part of the growth rate is positive or negative. If it is positive for one of the modes, we say that the solution is unstable, because it's sufficient that one of the modes grow for the solution to be distorted from its initial nominal shape. But if the if the growth rate decay for all the modes, then we say the solution is stable. Okay. So now what we want to do is, for our system, the analysis is simple, because d by dy just give you iky times the function. D by dt just pull out an omega because of the exponential nature. So when you substitute the equation, you get a system of ODEs with jump relation, and you can solve them. Before doing this, or before showing the result, I want to make two comments. First of all, note that when all the disturbances vanish, of course, you have a zero solution. In other words, no perturbation should be a solution of your system. Therefore, the question that you ask is, are there a non-trivial solution? And so the problem that we are facing, it's an eigenvalue problem. The other solution, or if solution exists, they will exist only if omega has a special, or takes a special form. In other words, there will be a functional dependence between the parameters in the problem, the wave number, and the growth rate omega. By the way, I just want you to remember, or you can see that by looking at the equation, that the problem under consideration in that limit that Darien and Landau have looked at contain only two parameters: the flame speed SL, right, and sigma, the density ratio. Those are the only two parameters in the problem. And therefore, the dependence of omega will be on these parameters, and of course on the wave number k. Okay, this functional form, if you can write it as omega equal to omega of the parameter, is often referred to as a dispersion relation. It tells you how the waves are dispersed. Okay, now in the case of our problem, I can roughly, very quickly tell you what the answer will look like based on dimensional analysis. And it's written here. Omega have units of 1/2, SL units of centimeter per second, K is the wave number 1/centimeter. So the only way to form a combination of this type will be that omega will be proportional to the flame speed times K. But the only problem is I don't know what the constant ahead. In fact, is it positive or negative? So we have to do the analysis. It's not sufficient to know the dependence from the dimensional none. Nevertheless, it's important to realize that. Okay, it suggests also that you can rewrite the problem in dimensionless form using SLK as your dimensionless growth rate. Okay, so before I do the problem, I want on purpose to do it for a very special case, one that the gas density or thermal expansion is weak. In other words, sigma minus 1 is small. I'll call it epsilon. If the density ratio is small, the velocities are going to be small, and the perturbation of the flame will be small, and the growth rate will be small. And so this is the proper scaling that you get. The advantage of this limit is that this term, which has an omega times u, will become epsilon square, right? Epsilon and epsilon square, and so it will be negligible. And so you will end up with a slightly simpler system, okay? So suppose we focus on this system. The first equation can be easily solved. The two solution is an exponent e to the kx and e to the minus kx. E to the kx cannot survive in the negative region for x, because then it blow up at infinity, so you eliminate it. And e to the positive kx cannot survive for x positive, so you kill it. So there is only e to the kx here minus kx here. The two constants are not known. Then you go to the equation for u. You see that u is essentially like p by differentiation. So here it is, with the exception of a minus. And then v is going to be the derivative of u divided by ik, so you compute it. Now you want to satisfy this condition. U doesn't jump, so C1 is equal to C2, right? And then P doesn't jump, so well, that's the same thing, C1, C2. But V is equal to minus IKSL, so you obtain that the C1 and C2 are 1/2 Ka. And so eventually what you end up with a growth rate which is 1/2 sigma minus 1 KSL. We knew that dependence. Now we obtain here the constant that I was missing for weak expansion. It's positive, which means that it's unstable. Okay. Of course, Dario and Landau did that for general sigma, and I will tell you the answer, but this is true for weak as well as for strong thermal expansion. The planar flame is unconditionally unstable. In order to understand this, I want to use some of the results that I have mentioned before about the perturbation of the velocity and the perturbation of the position, which I will quote in a minute. But before I do that, I want you also to note that when sigma minus 1 is small, the vorticity, which is going to be dv dy, dv dx minus du dy, is v prime minus IKU, and if you evaluate it here, it's 0 on both sides, on the unburned side and on the burned side. So here is the comment that I want to make. So if you remember, the first one of the jumps was that U prime is continuous across the perturbed flame, across 0 actually. Actually, I missed to emphasize that point. So let me go back for a second, emphasize this. Okay. So all the jumps, in principle, have to be evaluated across the flame. In other words, it should be those two green points, the one above minus the one below, right? Above the flame, below the flame. But the flame perturbation is small. And so by Taylor expansion, we can relate the point above to the purple point here above the line x equal to 0 and the one below to below the line. In other words, effectively, we can write the jump relation across the unperturbed flame, okay? Which is mathematically equivalent to the perturbation across the flame itself. And that's why when you see here what I have shown is the jump across 0, right? So u prime at 0 plus, u prime 0 minus. Also, what we have seen is that it's equal to the propagation speed of the interface. So the flame front basically is convected by the flow. That's the statement from here. The other condition about the tangential velocity, we had that there was a jump. So there is a discontinuity in the transverse velocity along the position x equal to 0. But there is no vorticity anywhere else. Well, a location or a sheet along which there is a jump in tangent velocity and no vorticity everywhere else, it's called a vortex sheet. And so the disturbed flame is equivalent to a vortex sheet located at x equal to 0. What is the strength of the vortex sheet is here. Essentially, it's proportional to f sub y multiplied by sigma minus 1. Of course, the sign is important. So here is what you have. You have a perturbed flame, which is equivalent to a vortex sheet located at this red line. And let's examine the tangential velocity along that vortex sheet. So on this segment here, f is positive. The slope of f is positive. Slope of f is positive, meaning that the burn velocity is smaller, right, because of the negative sign, means it's smaller than the unburned. So the blue burn is smaller than on the unburned side. When the slope is negative, right, this is going to be positive, and so the velocity above is larger than the velocity below. And it goes the same in the rest of along the flame. So what does that mean? It means that there is a vorticity here which is counterclockwise, and here clockwise. So you see the two vorticity just cause an induced flow which push the flame. Remember that any axial velocity just convect the flame. So it convect the flame upward. In this direction, it convect the flame downward, so it create that instability and it never go back. In other words, it's not damped, and it is the source of this so-called Darry-Landau instability. Now, I showed you this for a small expansion. Of course, you can do the calculation for any sigma. What you have is the additional terms here, which in fact says that there is vorticity in the burn gas. In other words, the vorticity created, it's still transported along the burn gas. By the argument that I made before, I couldn't say a priori if the vorticity in the burn gas is going to cause any decay or not, but clearly it doesn't, and the end result is the growth rate that we see here. What you end up is with a quadratic equation or a dispersion relation of the form shown here. When sigma is close to 1, of course, this bracket becomes sigma minus 1, like I showed you earlier, and it's multiplied by the speed times the wave number. We call this the omega Darry-Landau, just the growth rate, the Darry-Landau growth rate. By the way, there is a quadratic equation, means that there is a positive and negative root. The fact that there is a negative root doesn't mean anything, because there's always a positive root, which means there's always an instability. So Darry and Landau have shown that in the 1940s, and of course that created a problem, because then what does it mean? Flames are always unstable. Part of the implication of Darry and Landau was that therefore flames are necessarily turbulent, but this is not quite right, as we will see later on. So this is another way of explaining the instability. You focus on a certain stream tube. Since far upstream and far downstream, the area should be the same. And since there's an expansion here in the tube, the velocity have to be slower by Bernoulli's law. And since it is slower, and since the flame propagates at its own speed, it's going to propagate faster. And so again, it causes those dips to propagate into the unburn faster, and those dips propagate slow. Which argument you like, it's up to you. I like the former. It's more, it seems to be more descriptive. Both of them has the people like sometimes to give those arguments a priori, but unless you do the calculation, you're not always sure that those arguments are correct. And there is always a weakness in each of the argument. Here, I apply Bernoulli's theorem, but the problem is an unsteady one, and I apply the steady Bernoulli equation. So so it can be applied only in a quasi-steady sense, which is the same as I did before. I assume a weak expansion. So anyway, that's detail. The instability is stronger as sigma increase, and as a function of k, the growth rate keep on increasing. So the small waves, which are the large k, in fact, increase faster. But we know that the results are not valid for very large k. In other words, when you come to wavelengths which are of the order of the flame thickness, the results should fail. And at the time, there was no resolution for that question. So here is a few of the consequences of the Darry-Landau instability. If you start with a sinusoidal flame as the blue curve on top at t equal to 0, as you advance, since the flame propagates always along the normal at a constant speed, clearly the convex section towards the unburned gas is spread, but the concave form a cusp. And so one of the signature of the Darry-Landau instability is the formation of these very sharp cusps. You can see them experimentally. This is a V flame. Remember I told you that we can stabilize a Bunsen flame, an inverted Bunsen flame, by a rod at the center. This is exactly what was done here. The flame was seeded with some oil that was seen only in the unburned side, because they were essentially burned and so they don't exist on the burned side. So that clearly showed the flame front between the unburned and the burn. And you see that the flame front had developed these little cusps along the flame surface. This is another example taken from an older paper that in turbulent flame very often these folds and creases are created, and it's believed to be associated with the Darry-Landau instability. I mentioned briefly this before. If you look at a Bunsen flame and you reduce the incoming flow, eventually you expect the flame to become flat, but it never does. It always has this cusp-like structure, and again, that is a result of the instability. Similarly, flame in tubes are known to be curved, and they are curved convex towards the unburned gas. Again, could be attributed to the instability. A couple of other things that I want to add is the effect of gravity. So far, we have neglected gravity. Now, if we include gravity in the analysis, then, well, the question is, where does gravity come from? Because in the momentum equation, what you have is rho times g, just as a force. And rho is one value above, one value below, but that also what you get in the basic state, right? You get this hydrostatic pressure here and here, but with different densities, okay? But when you perturb the equation, where does the gravity comes about? Well, it comes really from the jump in the pressure. And because there is here different contribution, and so that provide an effect on that's a detail. If you go through the analysis, what you would obtain is similar to before, but an additional term due to gravity. So it appears as a Froude number, but I put it as G because it's more illuminating. So we can very quickly look at two situations, short waves and long waves. By the way, the flame is also always unstable, even with the inclusion of gravity. However, what we want to study is what is the effect of gravity? What does it do? So on the short wave, which is k very large, what you see when k is very large, this term here with gk is negligible compared to the k square because it's linear. And if it's negligible, you obtain exactly the Darry-Landau result. So short waves are really not affected by gravity. The influence of gravity die out as k become large. But for long waves, what you see is that then long wave k is small, so the k square is negligible. So the first term has this minus sigma square minus 1 gk. Of course, sigma square minus 1 can be factored as sigma minus 1, sigma plus 1, so one of those is gone or something like that. Oh, no, it's brought in inside. But anyway, the key thing is that if G is positive, then this is purely imaginary. And then you have to compute the next term because you are interested in the real growth rate, the real part of it. And the real part of the growth rate is negative. So it indicates that long waves are stabilized by gravity. But it's only if gravity is acting downwards, in other words, for a downward propagation. If I look at the opposite situation, and yesterday I mentioned that all it takes is just to change G to minus G to explain the upward propagation, then of course the sign, this is real and this is positive, and then it's unstable. So upward propagation will be further destabilized by gravity. Downward propagation, the long waves are stabilized by gravity. Questions to address? 4:15, right? Yes? Okay. So question, the Darry-Landau instability is a long wave instability, valid for when the wavelength lambda is much larger than the flame thickness. So what are the influences of diffusive effect that are occurring inside the flame on the instability? That's the question that Markstein started or tried to investigate. And then the next question is, the Darry-Landau results are based on a linear theory, small perturbation. So what happened once that the flame become unstable? As I said, they seem to have, even though they didn't explicitly say that in their paper, they seem to have indicated that they seem to believe that as a consequence, the flame is always turbulent. But this is not exactly the case, as we shall see soon. The next question, what is the influence of the Darry-Landau instability, let's say, on turbulent flames? And that's another question that is of interest. So, thermodiffusive instability. This is the next quick topic that I want to cover. So, well, it's difficult because, again, we don't have a way to grasp a simple solution to perturb. And so what people have done, they say, okay, you see the hydrodynamic instability get weaker and weaker when sigma goes to 1. In other words, when the thermal expansion is small. So let's filter out the hydrodynamic disturbances by taking sigma to be 1. In other words, by assuming the so-called constant density approximation. So if you do that, then you led only by a system of a reactive diffusive system, only two equations, reaction diffusion, and the only convective term here is just a uniform flow. So what is wrong about this clearly is what you are assuming is that the perturbed flame, So if this is the perturbed flame, what you're assuming is that the streamline are just parallel and uniform throughout, and of course that's not real. But that maybe help to understand the diffusive thermal effect. Okay, so what we have now is a temperature and mass fraction, and we want to write, first of all, the solution for a planar flame, which we did, and then perturb it. So, well, these are the two equations in dimensionless form. The important thing I want to emphasize here is that there is only one parameter left in the problem, well, two maybe, but one, which is the Lewis number. I said two because there's a Zeldovich number, but that is typically large, and we are going to use the fact that it's large, so it's out of the parameters that dictate or not stability. So there is only one parameter. So now, and the Lewis number, if I look at this system, Y must be the deficient component, because that's a component that when it's totally consumed, the flame, the reaction stops. So the Lewis number must be the thermal diffusivity of the mixture divided by the mass diffusivity of that deficient reactant. If I use two components, then I can also incorporate what I have earlier said, the effective Lewis number and so on, but the early studies just use one component. Okay, so it's going to be a fuel in a lean, the oxide-enriched mixture. All right, so here is the activation. Of course, even this system of equation, we don't have an exact solution, so we're going to use the activation energy asymptotic solution that we derived earlier this week, which is written here. It's an exponential on the unburned side, then the adiabatic temperature, and then, so there are discontinuity here, and we know how to treat the reaction sheet. We learned about this before, so that's what we are perturbing. And here is the basic state, perturbed. So now I just call phi and psi the perturbation, okay? And again, I am assuming a normal mode, e to the iky plus omega t. And you see here I have drawn the streamline to show you what I just said on the blackboard, that they are assumed not to be affected by the combustion. And F is the flame shape, which is of this form. Okay, so it turned out that the proper way to do this analysis is to also assume that the Lewis number does not deviate very far from 1. It turned out that this is only a technicality. In other words, that really doesn't restrict the answer too much, because even if you take Lewis number sufficiently large on one side or another, the result remain correct. So anyway, the idea is now is to find the dispersion relation, which is a function, the growth rate as a function of the only parameter in the problem, which is the Lewis number or the deviation of Lewis number from 1. And you crank through the analysis. It's not as simple as the previous one, but it's not that difficult. And you end up with a dispersion relation, which is a cubic equation. And all these coefficients, B0, B1, B2, B3, are only function of the parameters L and K. They are all positive, and we have explicit expression for that. I didn't write them because it was not very illuminating. Essentially, this was obtained systematically at the first time by Sivashinsky. And the next discussion is, of course, we have to take the growth rate, split it into real and imaginary part, and see when is the real part is negative, it's stable. When it's not, it's unstable. This is the answer. So this is the split of the now, right. Oops. Okay, so when we split this equation in real and imaginary form, it turned out that there are two places where the dispersion relation, the real part is 0. and there is one, the red curve, and one is the blue curve. The red curve satisfies this relation, and the blue curve this relation. They are both like almost like a parabola. This is a parabola, and this is a parabola if you think of it in terms of k squared instead of k. So, and in this region, which is a region surrounding little L0, which means unity Lewis number, the flame is stable. There is an instability here and an instability here. In both cases, the real part grows. The difference between these two is that along this curve, the imaginary part is 0. Along this curve, the imaginary part is not 0. And so here are what the growth rate as a function of the wave number look like as you cross this -2. So when you are on the right of -2, L is bigger than -2, the flame is stable, the growth rate is negative, the real part. When you cross it and you're on this side, so you have a growth and then it decays. In other words, there is a range of wave number, which is this range, that are unstable. Okay? Since there is a range, then the flame is unstable. On the other side, it's a slightly different look of the growth rate as a function of k, but basically there is a critical L above which there is a range of wave number which are unstable. So anyway, in short, the flame are stable when the Lewis number is near 1, but become unstable when Lewis number is less than 1 or sufficiently bigger than 1. Of course, we want to understand the nature of that instability. So here is the functional form that describes the flame shape, right? A e to the I k y omega I t, and I have set the omega r equal to 0 because we're focusing on a near neutral condition, namely just at the border. So you can have a situation where omega I is 0, and then F has the form e to the I k y, which is like a sine and cosine in y, which is like a cellular structure. Or you can have a situation where omega I is not 0, which was on the right side, if you remember, and then depending on if k is 0 or not. If k is 0, then the only thing that you get from here is e to the I omega I t. It means that the function f is a cosine sine in time, but k is 0 means it's flat, so the flame just pulsates. And if k is not 0, then what you have is you have like cells, but you have waves that propagate along the surface. So you can have all these situations. By the way, often this is referred to as a Turing instability, because Turing, even though he's famous about inventing essentially computers, he also did a work on a biological system where different diffusivity caused an instability of this kind. And so, and I think it was the first of such paper that was published in that area. Okay, so so this is essentially what we have learned from the system, that we have steady cells would be observed when the Lewis number is sufficiently less than 1, and either pulsating or traveling waves when the Lewis number is sufficiently larger than 1. Now, this number for Lewis number is quite large and rarely obtained in combustible mixture. In other words, it's rare that combustible mixture has a Lewis number which is that big. And so just freely pulsating flame are rarely observed. They have been observed in the lab when the flame is on near a Bunsen, near a burner, like a flat burner, due to the heat loss. Because what happened is that heat loss just bring down the critical value. I think it's mentioned in one of my other slides. You're going to see it in a minute. I'm almost done here. So this number goes down when there is heat loss, and so you can observe that instability. So anyway, this was just to explain the nature of the cellular flame. It's very difficult to explain the pulsation because you have to talk about time scales and so on. It's not simple. But the idea is that here is a planar flame, so the isotherm are all parallel to each other. When the flame is perturbed, then the isotherms are deflected, but eventually, if you go sufficiently far to the unburned gas, they'll be flat again because the temperature is uniform. So what you see is that you have regions, like a region which is convex towards the unburned gas, then you have high gradient. Now, the high gradient is depending on the Lewis number. If the Lewis number is less than 1, which means that the thermal diffusivity is smaller than the mass diffusivity, then then you have yeah, sorry. I was thinking about this, but looking at the wrong thing. So the thermal diffusivity is less. The thermal diffusivity is the heat conducted away. So this arrow is smaller than the mass diffusing into the flame. So since this arrow is bigger than this, then what happens is you get more fuel coming to the flame, and the flame is enriched and want to propagate faster. So it propagates. So this segment propagates faster. In this region, the gradients are weaker, and so it propagates slower. So you will find a situation where it propagates faster here than slower here, and it will maintain that cellular structure. There is a slightly different way to explain this, and this is transverse gradient, but it's the same idea. So before I stop, I just want to say that if you take the Lewis number, let's say, of a propane-air mixture, and you consider from lean to rich condition, then you're going to see that for propane, the Lewis number go from high to low number. For hydrogen, it go from low to high number. In fact, we have seen that before when I plotted the Markstein lengths and the equivalence ratio and so on. So the critical Lewis number for the onset of cellular flame seems to agree in general with the experimental observation, because for hydrocarbon air flames, cellular flames are usually observed on the rich side of stoichiometry when the Lewis number is sufficiently less than 1. For hydrogen air, it's usually observed on the lean side of stoichiometry, and that fits with this picture. One last quick comment that comes, you see, the analysis can also tell you more than just condition. For example, you can obtain an expression for the flame temperature along the surface, and what you see when you examine here the signs, you will see that it's usually weaker here at the crest and at the troughs, and so that's also what is observed experimentally. Okay, this is a picture due to Markstein. And finally, I was just saying something about the pulsation. I told you that the critical number reduce when you introduce heat losses. So when you have heat loss here, you see that that number that was quite far now becomes here. So this is the range of the stable flame, and so it's easy to go from here to slightly to the right and observe this pulsating flame on a burner. All right, we can take a break at 15 minutes, and then we'll talk about the consequences of these instabilities and so on.